Okay. Sorry. We're still in module number 3, renewable energy and solar radiation. Today I will start with solar radiation. Solar, starting from the principles, concept, as you can see, parameters, equations, and so on. And then we will move to the solar collector and then solar system. We will solve different problems related to the equations we are going to deal with. Also in tutorial, you are going to see something similar and solve problem. So, but before I start with solar, you may say, why would we focus on solar? Actually, because in Oman, particularly talking about Oman, in Oman, the priority for renewable energy is solar and then wind, and other renewable energy came. This is based on a study published in 2008 by Authority of Electricity Regulation. They make a priority solar and then other renewable came at the second, third, and so on. Now, today I will start talking about the solar radiation, how we calculated, and then I will tell you the story where I'm taking you in the next few weeks. So, solar radiation, as you know, in the sun, different reactions happen there, and it produces a massive amount of energy, heat and light. And this heat and light came from the sun to the atmosphere, to the ground, to my collector, and then I produce energy in different way and I give it to my load. So the journey will be through the sun to the atmosphere, to the land, to the collector, to the load. And part of the spectrum we are talking about, by the way, when I say spectrum, if I just bring my pen. Okay, as you can see here, when I talk about spectrum, this spectrum, similar to any bell shape, okay? Any bell shape in this way, this represents the spectrum. Part of it, which is in the middle here, called visible region, which is in the range of 400 to 750 terahertz. This part can be seen by eyes. And there is infrared radiation and ultraviolet, the other parts, I mean here, this part and this part, okay? And when we talk about, as example, if I classify them, I will say here visible, which is this range, okay, 400 to 750, it's produce around 44% of the spectrum. And infrared and below, which is lower than 400 terahertz, around 46, and ultraviolet, the small one, which is around 9%. So these together represent this spectrum for solar radiation, the light coming, the energy coming. Okay. Now when we look to the sun here, okay? And this is the atmosphere, and this is my planet, the Earth, okay? In the sun itself, 1,360 watt per square meter is the amount of power density produced. We call it solar constant. As you can see here, it's solar constant. It's the power density. Now, it represents the amount of power, or let me say, sometimes they call it energy flux. If we multiply by hour, so it will be energy rather than its power in watt. Now, this solar radiation contains two things, heat and light. We will capture heat and light in different systems or mixed together in one system to produce different type of energy. It could be electricity, it could be heat, as example, heating air, heating water, producing steam, and so on, for many applications, small, medium, and large applications. We will deal with this energy. Later on, I will show you that we will deal using Planck law. This is a Planck law, which is rate of change of energy with respect to frequency. And by this expression will be discussed when we reach to the efficiency. We will use it. I will explain it, each item. But here I just would like to mention, just simple mentioning here. You see it's related to frequency and to temperature. These are the main variables, but mainly frequency. So frequency is a many player, and the same Planck, if it's represented as a power density, this is the same previous expression, but rather than it is energy, it will be power. You see, again, it's not only for frequency, related to frequency to power 3, as we will see later, okay? So triple the frequency of the solar radiation came. or received. The same formula here could be converted from function of frequency into function of lambda, the wavelength. Okay. Now we will discuss Planck law and how we use them there in another maybe 2 to 3 weeks. We will discuss them. But just here I would like to mention. Now the spectrum, solar spectrum, if we want to have a look at it, we will see that it's variable, fluctuating. It's not smooth, similar. I mean, if I compare it to black body with 500 or 600, 5,000, 6,000 Kelvin, okay, black body is just body have a specific amount of energy, observing energy. You can read about it in Wikipedia. I make here some links you can see in my slides. You just need to follow if you want to expand your information. So this is the black body, if you can see here in this graph. It's just smooth. I just want black body close to my solar radiation to compare with. You see now the solar radiation. It's not smooth. It's fluctuated, as you can see here. It's not smooth, but it's close to the 5,000. 5,000 Kelvin give you indication about the solar radiation spectrum in which level we are talking about. And this part, from as I mentioned, from 400 to 750 terahertz is the visible. Here, infrared radiation. And here ultraviolet part. We will use some constants. I listed here some of them as example. Boltzmann constant is value. You can pick them directly. Charge of electron. You can as example Planck, as we will use it later. Constant, speed light, Boltzmann constant. We will use some of them. If you would like to read about this in international system, you can read them in this link. I put it for you. Now let's start. After this discussion, or let me, before this, since I have space here, I will use it. Have a look. Now this is my sun. We mentioned power density, or what we call a solar constant, is 1,360 watt per square meter. Actually, the real number is 1,357 and up to 1,362. In this range, but to make it simple number, they approximate it to be 1,360. This solar radiation came through the space until it reached, okay, the atmosphere. Now, atmosphere, I will talk about it at the end of the semester when I reach the climate change. But just a quick tip here. Atmosphere, it's, let me say, like imaginary line. You don't see it. It contains some gases with a specific percentage. As example, CO2 and OX and so on. So this represents barrier between the space and the internal sky of the land, of the planet. Now, when it reaches here, it loses 1/3 of its value. So it reaches here, it becomes 1,000 watt per square meter. So we lose 360 in the space. Now, my land here, okay, let's see. I'm here, okay, standing here on the land. The solar radiation approaching me here is related to many parameters. It's not that the 1,000 will be reduced definitely, but many parameters specify how much energy I will receive, or if it is collector, how much energy my collector will receive. Okay, this parameter, what we are going to discuss today, to see how much energy approaching my collector, because later on I will calculate this energy and introduce it to the collector, and from the collector I come up with another type of energy approaching my load. So we want to know how much we got from the solar energy. Now let me start with definition for the insulation. You know insulation, insulator as insulation is the power density of the solar radiation. We call it insulation. Okay. Now, as I mentioned, solar constant is 1,000. So when it's approaching the atmosphere, it becomes 1,000, which is called one sun. We call it one sun. And you can see here these maps, this one and this one. You can see the colors are different. The color represent the amount of solar radiation or insolation in this region. Some region are you can see dark red. Some of them are blue. Dark red, it means high, or let me say potential of solar energy. Blue, less energy. As example, in this region, in Oman here, you see Oman on the map here, it's red. So we are talking about the high value of solar radiation. So there is potential, which is good. Well, if you go to the north of the planet, Europe and so, you will see that less amount of solar energy is there. The potential is low, but still people are using this. Now, you may say, okay, what are the, let me say, parameters specify the amount of solar insolation approaching my collector? Two things: orientation, how we orient our system, and the second issue is the transparent, the sky, what is inside the sky. Definitely, we will have some sources of errors in our calculation. We need to consider 4 errors I will mention here. The first one is we assume the period between successive sunrise is constant. It means from sunrise to sunset, the day is constant through the whole year, which is not correct. Usually, as you know, in summer, the day is longer than night. In winter, the opposite happens. Day is shorter than night. As example, maybe in summer, you have 12 hours. The day is 12 hours. I'm talking about when it's shining, okay? While in winter, maybe it's 8 hours only. So this assumption is not accurate. So we have to modify it, to rectify it. We will see later, we will use what we call it equation of time to rectify this. I will talk about it and give example. The other issue is we use mean local time. Okay, mean local time, I mean, our watch is here. We use the time as example. Now it is 10 past 9. Okay, around 10 past 9. This is not accurate time. This is approximate time. Why? Because we assume here, when scientists make the time for our watches and so, they assume the hour is constant through the day, constant through the year, which is not correct. Okay, there is different from, by the way, how we measure the time. If you know, if we would like to measure the time, we measure it based on the Earth, the planet, and the sun, and the relationship between them and the movement. Okay, and we classify it into seconds, minutes, hours, days, weeks, months, 365 days per year, and so on. But it's approximate. Why? Because they cannot say, okay, the hour could be 60 minutes sometime, 58 minutes sometime, 63 minutes sometime. They want one number for hour and that's it, done. Okay, so this is not correct. We have to rectify it. We will rectify it using what we call it time offset. I will explain it later on. Okay, the third error here also is the geometry of the situation, of the site and situation. What does this mean? This means, as example, when sunrise, okay, before I see the sun, I see there is light, because our planet is a sphere, okay? So I see the light before I see the sun. And when sunset going down, it's go down, I don't see it, but I still see the light for a while, even if it's small short of time. This means that the geometry is not 90. I mean, when I talk about example, this is the vertical and this is the horizon, okay? The sun is coming from here. If you can see me, let me see, where is it? 1 second, I want to see if you can see me or not. Okay, you can see me. Okay, if this is the vertical and this is the horizon, okay? Sun rise from here and rotate until it become in the middle of the day, midnight, midday. This is okay. Afternoon go down until it reach from the other side, sunset, and it go down, so I can't see it. Okay. Now here from sunrise to the middle of the day, 90 degree, and this is not the truth, because sunrise is not here exactly. It's below when I start seeing the light. So this needs to be rectified. So this is not anymore 90.83. And the last point here is the transparent. Transparent, I mean, usually when people do calculation, they assume that they have transparent, let me say, sky, no clouds, no pollution, no dust, no shadow, nothing at all. Okay, which is not the situation. Okay, the situation is for some countries, As example, in Europe, in UK, I live in UK there, it's clouding most of the days of the year. So you can see that it's a cloud. I mean, cloud is a big barrier for the solar radiation to reach your collector. Also, dust here as example, in this region, the problem of dust is clear. It's sometimes dusty weather, so it's make a shadow on the collector. So solar radiation have difficulty to approach my collector. This need to be considered. How we consider it? All these will be translated as equations, formula. We will use them to do the calculation. Now, after this introduction, let me start with the parameters. The first parameters I will define is zenith angle, as you can see here, represented by this Latin symbols, and azimuth angle. Okay, what is zenith angle? Have a look. I will explain it on this figure. I have give you different figures, but this one is easy to explain. Now, my collector here, okay, in this point, in this cross. This is the zenith, the vertical line, okay, and this is the sun. I make a line from the sun to the collector. The angle between the zenith and the sun, we call it zenith angle. Similar to this one. This is the zenith, this is the sun, this is zenith angle. If I talk about satellite here, satellite on the other side, okay, the angle between the line from the satellite to my collector here and the zenith, we call it satellite zenith angle. You got it? So this is the angle between the line between sun and the collector and the vertical line. This is called zenith angle. Azimuth angle, okay, it's measured anti-clockwise, okay, meaning from the north to the east, south, in this way, in this direction, okay, and I explained it in the other slide, in the next slide, because I will show you a figure to explain on it. But before I go for this, I would like to mention something. These functions, zenith angle and azimuth angle, are function of time of the day of the year, and latitude. Time of the day, tell me, it's 9 o'clock, 11 o'clock, 13 o'clock, okay, 17 o'clock, what is the time? We need to know this. Day of the year, is it day number 1, I mean 1st of January? It is day number 15 of January. Is it day number 32, I mean 1st of February, and so on? Because we have 365 days per year. So tell me which day. Also, latitude. You know, we know the location on our planet using latitude and longitude, as I will explain in the next slides. Okay, so latitude is also a main variable here to calculate zenith and azimuth angle. For azimuth angle, have a look here. These are different graphs, give the same meaning but in different way. But have a look here. This is north, south, east, west. Okay, have a look. Moving from this direction, clockwise. This is the sun. The vertical line from the sun to the circumstance here, and we make a line here to the center of the planet. The line from here to this triangle represent what? Represent the azimuth angle. Oh, so it seemed to be the zenith angle and azimuth angle, we are talking about different dimension. The dimension is different, as you will see later in some figures. Different dimension. Now for longitude and latitude, you know them, but it's good to revise them. Okay. Now for latitude, this is the equator. خط الاستواء, equator. Okay. It is at 0 degree. Now we go up here in this direction to the north or to the south. To the north, we're having positive. To the south, we're having negative values. Okay? They split, or let me say, distributed the regions here based on latitude lines, which is 15 degree. So this is 15, this is 30, this is 45, 60, 75, until they reach at the north here on the pole into 90. The same thing could be said, but in negative, going to the south. This is called latitude. Longitude, okay, we have this line which is called prime meridian or Greenwich, okay? Greenwich is in London, okay? If you go there, I advise you to visit. I will show you some photos later on, but it's the 0, okay? The 0 line. Also, they distribute the planet in this direction into lines. Each line represents zone, time zone for this. For each zone, there is time, specific time. Okay, so they started from 15 degree, 30 degree, 45 degree, 60, and so on. Okay, going up until they reach 180 at the pole. Okay, now each zone mean that we add 1 hour to the prime meridian, to the Greenwich. It means, as example, here 1 hour, at 30 another hour, at 45 another hour, at 60 another hour. And since Oman, okay, Oman somewhere here, okay, at the 60 zone, so it means that whatever the time in Greenwich, we add plus 4 hours. You got it? And if we go to the west in this direction, okay, to the west, we are dealing with negative signs. It means minus 15, minus 30, minus 45, minus 60, and so on. Okay. And you can see here, these are some photos from different direction for zenith and azimuth together. So you can imagine that we have different, let me say, dimension. I put here some website, you can read through them. There is some interesting information if you want to expand your information in this regard. Okay, now I define zenith angle and azimuth angle. Let's come to the time of the day. Okay, still these, don't forget where we are going. We want to define angles, parameters. We use them later on in equation to calculate the solar insolation approaching my collector. Okay, I want to know how much my collector will receive from the sun, from the 1360 watt per square meter, how much I will receive, okay, to do the calculation to find how much I will produce. I cannot use the time directly, but what I will use what we call it hour angle, represented by alpha. Okay, by the way, some textbooks have the same information, the same definition, but they use different, let me say, symbols. As example, we use here alpha. We use either Roman or Latin. Some of them they use phi and whatever h, okay, for to name these variables. But at the end, they are the same variables. Now, our angle could be calculated using this formula. If we calculate in degree, and this formula if we calculate in radian. In degree, 360 over 24 t minus 12. If we deal with 24 hours from 0 to 24. And this value, this expression, if we talk about radian, some people deal in radian system, some people in degree, but usually we will work on degree. All the time we work on degree. Or this one can be simplified in another way and written this way, very simple. Our angle alpha is 15 per hour, number 15, multiplied by hour before solar noon. Okay. Now, if we, as example, if we say it's 9 o'clock in the morning, so from 12 to 9, how many hours? 3 hours. Then we multiply 3 by 15, 45. The hour angle is 45. If we say it's 3 p.m., it means 3 hours after 12, right? It is after the noon. So this means it will be negative, minus 3 hours. Minus 3 hours multiplied by 15, it will be minus 45. We'll explain this in the examples will be discussed soon. Now this is the hour angle. Again, don't forget zenith, azimuth, hour angle. I will add another one which is called solar declination angle. Solar declination angle specify the position of the sun or the energy coming from the sun based on the day in the year. It means we have 365 days per year. So which day we are talking about? Is it in, as example, when we talk about 15, that day number 15, we are in January. January usually is winter, okay? But when we talk about day number 120, we're talking about June, it's summer. The solar radiation in winter is different from summer and so on. So how we calculate it? This formula used to calculate, which say is 23.44 sine 360D minus 80. D is the day number from 1 to 365 divided by 365.25 degree. So we have now 4 angles defined till now, variables. Okay. Now let's come to really interesting equation. You will use it. We will use it in examples with me and with Miss Moza in tutorial. Now, what the equation say? So a cosine x, which is zenith angle, sine delta sine lambda plus cosine delta cosine lambda cosine alpha. Easy to remember. Okay, easy, very easy to remember. Sine delta sine lambda plus cosine delta cosine lambda cosine alpha. You can remember it very easy. Okay. Now here we can't calculate x, but we need to provide this information. We will see how we provide them. And another formula used to find azimuth angle. Tan azimuth is sine alpha. Please mute your mic. Please mute your mic. Okay. Sine lambda cosine alpha minus cosine lambda tan delta. Now one note here to be mentioned. Since we are dealing with cosine, as you can see here, cosine and tan, if we want to find x or azimuth, zenith or azimuth, we will do inverse. I mean cosine inverse, tan inverse, right? Sorry. When we do inverse, we expect to come with two angles, right? You remember, let me remind you with foundation. In foundation and the secondary school, okay, you are here. This is the 360, this is 90, 180, 270, 360 back. Oh, back. Here all positive, sorry. Here only sine positive, cosine positive, or tan positive, sorry, and here cosine positive. You remember this. So when we say as example, it's cosine inverse and it's positive, so we have angle here and angle here. When we say sine inverse is positive, we have here, or negative, we are here and here. So always we have two values for when you do inverse. Or you can use this formula, this table. This table say that when the angle Reem, please mute your mic, okay? Okay, so if you have alpha and azimuth, their signs are positive, then you use this formula to find the angle directly, or positive, negative, this one, so on. Negative, positive, or negative, negative. You can use this table. Another formula, by the way, could be used for finding the azimuth angle. Rather than tan azimuth, it will be cosine 180 minus azimuth. You can find it through this formula. So you have the formula. You just need to provide the information, substitute the formula, get the angles, and then use the angles to calculate the insulation, as I will show you in the next few slides. Now, you remember the slide I mentioned that I mentioned cosine zenith angle equals sine delta sine lambda plus cosine delta cosine lambda cosine alpha. You remember this formula in the previous slide. At sunrise, when sunrise here sunrise, and here sunset. In sunrise, the angle is 90. Now, if the sun here, okay, and this is the zenith, the angle between them is 90, right? So if I substitute here 90, cosine 90 will be 0. Take this to the other side, it will be in minus. Divide and simplify. We got this formula. Which say cosine alpha for rise or for set, they are equal, because also from the other side it's 90, equal minus tan lambda tan delta. Very easy, it's simplified. So if I have delta and lambda usually given to you because they told you that this is the location, they give you lambda. And delta, if they tell you the date, you can't find it, you can't calculate it. I gave you equation to calculate. So directly I can find alpha for rise and set. For alpha for rise, alpha for set. As I mentioned, before noon, positive, afternoon, negative. Okay. Now, after we define zenith angle, azimuth angle, hour angle, declination angle, declination angle, then we can go to see different collectors. By the way, till now, I didn't talk about collectors. What type of collector? Is it solar cell? Is it solar thermal? What type of collector? I will show you there. We have different type of collectors. But until now, we are defining the information there to come to the insulation, to calculate the insulation. Insulation, we have different type of collector. Based on the collector, we have different formula. Have a look here. If we talk about insulation on sun tracking surface, what the meaning of sun tracking surface? Have a look. Let's assume this is the sun. My hand is the sun, and this is my collector. When the sun moving, collector follow the sun. Why? Because we want to make sure that the sun solar radiation is directly focused on the collector. Yeah, you may say, but when we move it, we're losing power because we move it through motors. This is something else. We will talk about it. But now, moving, some systems are movable. Okay, in this way, we have in our lab in Sohar University on this building, on the top of this, we have something similar, sun tracking surface. And if we want to calculate the daily average insulation, we will use this formula, 1/T integration, the power density, which is, let me say PS, let me say sun, okay, which is 1000 watt per square meter, from sunrise to sunset, okay? And let's hypothetically assume that the solar radiation is the same through the whole day, which is not real. It's not realistic, but let's assume. Then when we integrate, converting sunrise to sunset time into hour, because we don't deal with time directly, we deal with hour angle, and substitute, we will find that it become 1/pi alpha s ps. Forget this is constant, so only we have alpha s. Oh, this means when we talk about calculating the insulation for surface or collector, which sun tracking collector, the only variable here is alpha, which is the hour angle. It's only related to the time of the day. At what time? Because the position of the sun with respect to the planet give different amount of energy. You remember, this is a spectrum, okay? The spectrum have different, and if we plot the spectrum through with respect to time, this is the middle of the day, and this is here, let me say 8 o'clock in the morning, this is 8 afternoon or evening. So in the middle of the day, the solar radiation is the highest. I will show you this some graphs here. One point to mention here, if we are in the equinox, what the meaning of equinox? The weather is neutral, is let me say nice weather. Let me say talking about 21 to 23 of March, 21 to 23 of September. Okay, we call them the equinox. Then delta will be 0. Why? Because it's day number 80. 80 minus 80 0, so it will go to 0. Delta, the whole expression will go to 0 when I substitute the previous formula. Okay, so only alpha, and alpha will be pi/2, because when I substitute, remember we say cosine alpha equal minus tan delta tan lambda. When this is 0, this is gone, and then alpha supposed to be pi/2, because if this is 0, then alpha should be 90, so the equation will be correct. So when I substitute here by 90, which is pi/2, pi with pi, what is left? PS/2. So this is the highest. It means 500 we can have, but this is still talking theoretically. Okay, keep in mind, for tracking system, only alpha is the player here, the variable we need to consider. The other collector is the stationary surface. Stationary surface, most of the collectors available today and their applications are stationary surface. It means we fix them in this way with an angle, small or large angle, doesn't matter, but we fix them in an angle. You see here as example, this is my collector. Okay, now I will define a new variable, which is epsilon. Epsilon, we call it elevation. Okay, elevation, or we call it tilt angle. If this is the collector, the sun is here. Okay, then the angle between the horizontal here is epsilon. Okay, we'll call it tilt angle or epsilon. Now it's coming here to be used when we calculate the insulation. It's one of the variables to be used. P insulation, PS, which is as I mentioned 1000 watt per square meter, is cosine epsilon cosine z x, sorry, which is the zenith angle, sine epsilon sine zenith angle, cosine azimuth minus azimuth of the collector. Okay, this is azimuth, which is either 180 if we look to the south. As example, the equator is here. The part of our planet to the north, we are in the after the equator, so we are in the north. We have to face the south. Exactly. This is the north in Oman, and this is the south. So my collector should be in this way, facing the south. If we go after the equator, okay, below to the south, then we have to face the north in this way. You see? So look which part of the planet you have your collector. So if it is as I mentioned to the south, then 180. Okay. Now here I gave you some values just to have an idea about average daily solar insolation. Okay. You can see in watt per square meter. Here are the different cities from US, Los Angeles, California, and so on. You see the values in this range: 170, 140, 180, maximum to 180. These are their values. Okay, so we don't expect that from the 1000 we have high values. Now, last one is the horizontal surface. Horizontal surface, we put it in horizontal way in this way. Now, the sun is moving in this way. When it is here in this place, this situation is different from the middle. In the middle to be direct. Here, part of it will come, right? So the power or insulation, power density or insulation is PS cosine X. You remember cosine X? Sine delta, sine lambda, cosine plus cosine delta, cosine lambda, cosine alpha. When we integrate from sunrise to sunset hour, we substitute this one here, cosine X substituted here. When we substitute and integrate with respect to what? Our angle. Let's see, is there any hour angle here? No, there is no hour angle here. So it will be multiplied by alpha. Is there any hour angle? Yes, there is cosine alpha. When we integrate, it will be sine alpha. Okay. Now, when I substitute from sunrise to sunset, you can see this alpha. It will be sunset minus sunrise, and this sine alpha S minus sine alpha R. Simplify more. Okay. You remember we say that alpha rise equal minus alpha set, right? When we substitute here, okay, here minus alpha set minus it will be plus, so alpha S plus alpha S 2 alpha S. Okay, and the same thing here. This one minus sine alpha rise equal to minus sine alpha set, and minus will be plus. It's like 2 sine alpha set. So I simplify it in this way. You see, then I take the cosine delta and cosine lambda outside as a constant. Then I have to divide here by cosine delta cosine lambda. This will give tan. This will give tan. It will be here. You don't need, but just you need to understand from where it came. Otherwise, you will use the formula directly. Okay. Now this is the final formula. Okay. This is the final formula. How it look like. But I just explained from where it came. Okay. Now, at equinox, we mentioned that delta is 0. You understand what the meaning of equinox? Why delta is 0 and why alpha is pi over 2. When we substitute in this formula, we will find that the insolation is function of latitude. It means function of the position on the planet. Where is your planet? Is it in Suhar? Is it in Abu Dhabi? In China? In US? Where is it? Tell me the location. I will specify or find the power insolation or insolation, power density. If it is at the equator, no, yes, alpha still pi over 2, but delta have different value. It means based on the day of the year. So when I substitute there, I will find that the insolation is related to delta, to the declination angle. You tell me the day of the year, I tell you how much insolation. Now, after I completed this, just let me summarize what I discussed till now. I started with the solar energy. solar radiation, what happened on the sun when it comes from the sun to the atmosphere. It reduces from 1360 watt per square meter to 1000 watt per square meter, and then it goes through the space until we talk about errors. We define the orientation angles. These represent, and the transparent angles. These are the zenith angle, azimuth angle, declination angle, elevation, hour angle. All these have been defined, latitude, longitude. Now, then we discuss the type of collector: sun tracking, stationary, horizontal. Okay. Now let's see what are collectors we are going to deal with. The collectors we are going to deal with are either it's part of our architecture for buildings, or flat plate collector, or evacuated collector, concentrated collector, solar point in general. And by the way, some of them we are going to design later on to explain more with formula, equation, examples. But on some of them we just will highlight. As example, when I talk about architecture, in cold places we need to observe more heat to heat our places, our buildings, our houses. While the opposite happen in hot or warm weather similar to this region, we want the light, but we don't want heat. Okay, so how we play with this to get the useful or needed, let me say, energy from the solar radiation or insolation. As example, in some cold places we would heat, what we call heat storage. Heat storage, see example here, they make pipes similar to their cylinder with a fluid, water or anything. Okay, it absorbs more heat and absorb it fast and release it slow. So at night when it's cold, it releases it, so still the place is warm. In some cold places, as example, they make the wall here as example by using windows, okay, glasses, so light come on these, the ground and the wall and the roof. They make it from specific material which absorbs more energy. Okay, see this let me say cabin in Colorado, glasses, so they don't need artificial light. Natural light is coming at the same time, heat is coming and they capture it. Or let me say here, this in also Colorado, in the let me say in the valley, you can see here they make like umbrella here. These are well calculated, because what happened, the sun is high in summer. Okay, so we need umbrella to make sure that no more light and energy come inside, but it is low in winter, so more light and heat, because we want heat in winter but we don't want it in summer. These need to be calculated also, and they calculated using what they call it insulation. Okay, this is just mentioning. Okay, we'll not take example on this, but only one example. We don't need to spend much time on this. Now, you know the well of the buildings or houses or rooms or cabins. Okay, we need to know how much insulation will go through it. Okay, from outside to inside, because this specifies how much ventilation, how much heat we need in cold places, or how much cold we need in hot places. Okay, they define the heat power by lambda. Lambda here is used also, but not for latitude. It's used here for the heat conductivity. It's related to the material and the area of the wall and the temperature gradient. And when we put them together here, lambda A delta T over delta X, and we define R, okay, delta X over lambda, okay, it's constant because these are constant, okay, then the formula is related to the area and the rate of change of temperature from inside and outside divided by R. Usually you will find the textbooks talking about this, especially civil engineering people are dealing with this. They use British thermal unit or they use SI units. So if we are converting, we have to multiply. To SI unit, we have multiplied by 0.178. I will give example. Consider a house with inside temperature of 20 and attic temperature of 0. So directly we'll say delta T is 20 minus 0. Okay. The ceiling has an area 100. He gave me also ceiling. This is the ceiling area. Delta T, I got it. Okay. What is left? R. Also insulated with R. He gave me R. 11 material. But usually R given in BTU. So we need to multiply by 0.17 to convert into SI units. You see here, I multiply it by 1.17, I convert it into SI unit. The remaining is just multiplication. We got the heat power. Flat plate. I'm around to finish a few slides and we will finish. Flat plate, you may have collector in this way. It's sheet of any metal. It could be copper, iron, okay? And behind there are pipes similar to this, pipes, okay, attached directly, and they painted by color, as you can see here. This is the sheet, okay, and these are the pipes behind. When the sheet capture heat, it heat the pipes. When water or fluid follow through the sheet, the pipe, what will happen? we will heat the fluid, okay? Our students, Suhar students, okay, talking about maybe 12, 13 years back, okay, they manufacture it, okay? It was part of the course they manufacture, let me say, systems, solar collector or whatever it is, okay? These are mechanical engineering students. You see the pipe here, water follow through the pipes, is get heated, and then we store it in a collector or storage tank. I will stop here. I don't think I have enough time. Do you have any question until this point?